So picture this. You're completely off the grid. No cell towers, no Wi-Fi, yet somehow that little glowing screen in your pocket still knows exactly where you are. Today in this explainer, we're going to look up, way up, to uncover the invisible, continuously running infrastructure that makes this everyday magic possible. It's time to unlock the mystery of satellite navigation.
Section 1. The Offline Blue Dock.
All right, let's dive into this core mystery that I'm sure you've experienced firsthand. No bars, still located. You're out hiking, maybe driving through a totally remote area, and bam, you lose all cellular service, zero connection to the internet. But you open your map app, and there it is, your blue dot, faithfully tracking your every move. So how does a device with absolutely no network connection pinpoint its exact location on Earth? Well, to figure this out, we need to completely rethink how location actually works. Satellite positioning. It's a purely passive mathematical calculation. It is absolutely not an internet lookup.
Section 2. The Invisible Transfer Chain.
To really get how this passive math works, let's name the actors. First off, let's get our terms straight. We throw around GPS all the time, right? But GPS is actually just one specific system maintained by the US Space Force. The broader, far more accurate umbrella term we should be using is GNSS, Global Navigation Satellite System. Your modern smartphone is equipped with a GNSS receiver that listens to multiple satellite constellations from all over the world, not just the American GPS ones.
And the flow of information here, it is a strict one-way street. Let's trace it out. Step 1 is ground control. We're talking about stations scattered across the globe that monitor the satellites, prep their orbital models, and sync their highly precise clocks. They beam this data up. Step 2. The satellites take that data and continuously broadcast one-way radio signals back down to Earth. And Step 3. Your phone's GNSS receiver catches those signals and solves the math locally. Now, the absolute most crucial thing to grasp here is that these satellites do not ping your phone. They aren't tracking you, there is no two-way conversation, and they don't receive any requests from your device whatsoever. They are literally just lighthouses in space, continuously shouting out their location and the exact time. Your phone, it's just silently listening.
Section 3. Solving Space and Time.
So, if your phone is just passively listening to a timestamp and a location shouted from space, how on earth does it know where you are standing? Okay, you've probably heard the word triangulation in spy movies when they're tracking a burner phone. Yeah, forget that. That is a total myth when it comes to satellites. The actual term you're looking for is trilateration. Because these radio signals travel at a known rate, the speed of light, your phone can calculate exactly how far away a satellite is simply by measuring how long the signal took to arrive. Distance equals rate times time. This calculation creates a giant virtual translucent 3D sphere around that satellite. Your phone knows it sits somewhere on the surface of that sphere. Add a second satellite, you get a second sphere, and they overlap to form a circle. Bring in a third satellite, and now those three spheres intersect at just two specific points. One of those points is usually way out in deep space, and the other? That's your exact location on Earth.
But wait a second. 3 spheres intersect to give you your X, Y, and Z coordinates, right? Your latitude, longitude, and altitude. So why does literally every engineering manual insist you need a minimum of 4 satellites? Here is the absolute key to the whole shebang. Your phone does not have an atomic clock. Satellites up in space are equipped with incredibly precise atomic clocks that keep time to within billionths of a second. If your smartphone had an atomic clock inside it, it would cost tens of thousands of dollars and be about the size of a refrigerator. Instead, your phone rocks a cheap, relatively inaccurate quartz clock. Now, because our trilateration math relies entirely on the exact travel time of that signal, even a fraction of a millisecond of error in your phone's clock would throw your location off by kilometers. That 4th satellite signal provides the missing mathematical variable. It allows your phone's receiver to locally solve for what's called receiver clock bias, perfectly syncing your device's cheap clock with the atomic time of the satellites. So, 4 variables, X, Y, Z, and time, means 4 satellites are absolutely required.
Section 4. Separating hardware from software.
All right, now that we've solved the space math, let's bring it back down to that screen in your hand. There are 2 completely separate product layers operating inside your phone. On the hardware side, you have the GNSS chip. Its one and only job is to process those radio signals from space and spit out raw latitude and longitude coordinates. That's it, just naked numbers. On the software side, you have your operating system and your map apps. The software takes those raw coordinates and visually superimposes them onto the maps, the routes, and the traffic data you see on your screen. This separation is exactly why you still have a blue dot when you're completely offline. The GNSS hardware chip is still quietly doing the math from space. But if you didn't download the map data over Wi-Fi beforehand, your software has absolutely nothing to draw. You'll just see your blue dot floating in a void of blank gray grid lines.
Now you might be thinking, okay, but my GPS definitely locks on way faster when I have cell service. And you know what? You're absolutely right. This is a feature called Network Assistance, or A-GPS. See, downloading those precise orbital positions and clock data directly from a slow, faint satellite radio signal can actually take a few minutes. But if your phone has an internet connection, it can instantly grab that assistance data from a ground server, which drastically speeds up your time to first fix. But keep in mind, this network data is just a startup aid. It is absolutely not the core ranging link. The actual distance measurement, that still comes purely and passively from the satellites.
Section 5. Where the system fails.
As mind-blowing as the system is, relying on whisper-thin radio signals from 20,000 kilometers away definitely comes with some physical vulnerabilities. First up, we've got environmental failures. You'll often hear the typical smartphone accuracy is around a 4.9-meter radius. But, huge caveat here, that figure assumes open sky conditions. Because these are such weak radio signals, they're easily blocked by building roofs, thick concrete, or dense tree canopies. Don't expect this satellite positioning to work underground or deep inside a shopping mall. Plus, when you're in a dense city surrounded by skyscrapers, you run into atmospheric effects and something called multipath reflections. Basically, the signal bounces off a glass building before it finally hits your phone. Because the signal took a longer, bounced path, the travel time increases, the distance calculation gets messed up, and suddenly your blue dot jumps 3 streets over.
Beyond the everyday environmental stuff, we also have malicious failures. Let's quickly contrast jamming and spoofing. Jamming is basically just brute force. A local transmitter blasts loud radio noise on the specific GNSS frequencies, completely drowning out the quiet satellites. Your phone's signal-to-noise ratio absolutely plummets, and it just loses its fix entirely. Spoofing, on the other hand, is highly deceptive. An attacker broadcasts fake, perfectly formatted GNSS signals that are just loud enough to overpower the real ones. Your phone is tricked into locking onto the fake signal and calculates a false location. Now, some modern devices can actually detect this interference by monitoring something called automatic gain control. It's essentially the phone noticing when its radio amplifier suddenly has to dial itself down because a suspiciously strong artificial signal just blasted it.
Section 6. A durable mental model. Okay, we've covered a lot today. We've talked about the actors, the one-way data flow, the complex trilateration math, the separate software layers, and where things break down. If you take just one thing away from this explainer, let it be this highly durable mental model. Satellites broadcast, your receiver solves, internet accelerates, enriches, and shares. I love that because it perfectly captures the whole architecture. Space infrastructure is entirely a one-way broadcast. Your local device is the active solver crunching the math, and the internet, while totally not required for the math itself, is what makes the final experience fast, highly visual, and connected.
So the next time you completely lose cellular service, or the power grid goes down in your city, and you glance down at your screen to see that reassuring blue dot still tracking your every move, you'll know exactly why. It's not cell towers, it's not Wi-Fi. It is an invisible fleet of atomic clocks silently whispering their locations across the vacuum of space, caught by a tiny chip in the palm of your hand. Knowing all of that, how differently will you look at your phone the next time the grid goes down? Thanks for joining me on this explainer. Keep wondering and keep exploring.